for NS3 in general, scenario is just an application. It's just an application that uses NS3 frameworks by whatever means possible. And the usual structure is to define the topology, configure whatever parameters in ndnSIM. It would be configure content store, like installing NDN stack, configure parameters of NDN stack, like a FIP, strategies, and again, any updates for the content store. And then schedule the application, or schedule creation of the application at specific points of time, schedule specific events to happen at specific points of time. So this one you can do, kind of for the ndnSIM, this part you can do either directly using NS3 routines, so there is a special routine to schedule event inside NS3, or you can use the ndnCXX routines to schedule events. Like they're basically going to be equivalent within the simulated environment, with just exception that you can copy the same code for the CXX and run compile against the actual CXX and it do the work. You have to not forget to enable some kind of metric collections, or enable logging, or add anything like to print out a file, and then you run the simulation. And to run simulation, there is basically a small routine that you can call the simulator run, and it will just run simulated simulation for the specified amount of time, simulated time, or until all events in that simulation are finished. And the way you can create scenarios is basically twofold. I mean, there are probably more ways of doing this, but one basic way that was kind of highlighted as part of the NS3 documentation, you can put some of the scenarios in a Scratch folder. So for example, if I just go back to my folder, so this is highlight of the structure of what's inside NS3. Like this is NS3 itself, it's not even ndnSIM. So in NS3 there's a source folder and ndnSIM is somewhere here, and there's like modules of ndnSIM there. But there's also a special Scratch folder where you can put any C++ code that will be compiled as a scenario. And they already provided an example of the Scratch, I think it was Scratch simulator, that effectively does nothing but highlights the structure of the code, the very high level structure of the code. So you do a few imports, like in this case, it was just import for the core module. Whether you do the namespace and using namespace, it's up to you. You can enable logging if you really want to. This is, again, not defined. But in order to run the scenario, you just call the simulator run, and that runs the simulated scenario. Of course, in this specific case, nothing will happen because there's no events for schedule for the simulator to run, so it will exit immediately. For real scenarios, you just have to do more stuff in here and put actual, as I said, the topology, some other things, and those will effectively schedule some events to be simulated, and when you run them, the simulator starts scheduling events at the specific points of the simulated time. One option to create scenario is to put them in this folder and somehow manage them in this folder, and it works. It works. It works out of the box. You don't need to do anything. Unfortunately, it's not the best way. And one of the reasons it's not the best way is extremely slow. So for example, let me just modify. I think I modified a little bit in this file. Again, I just changed one file, already pre-compiled NFD because I don't want to waste anybody's half an hour to just look at how NS3 is being compiled. But you already see how much time it's taking to recompile one file. And this one is actually quite fast. And if I want to run it, so it's WAF run, and I think it's called Scratch Simulator. And hopefully it will, yeah, it did something, and NS3 log, and you can do all, and we'll probably produce some of the results, some of the login that something will happen. So in NS3, there's a bunch of these modules. For each of the module, effectively, there's a file called NS3 something-module.h. So these files are actually automatically generated. So if you build, I think they would be in NS3 module. So you can see there's a bunch of files. There's antenna module, UDV module, application module, and there's also ndnSIM module somewhere as well. So for each of the modules, if you want to include everything from that module, everything that was designed to be included as part of everything, you can just call this one. If you're planning to do a ndnSIM, so just ndnSIM module. Okay, and what I was showing before we just started, that if you run with all logins enabled to run Scratch simulator that doesn't do anything else yet except just starting simulator, processing 0 events and closing simulator, is still behind the scenes. It created a bunch of the objects, did a lot of stuff, and finished. Running this way is possible, not recommended at all. Again, you can do it. Like, this is the way I started. Like, whenever you're playing initially with things, you probably will do using Scratch stuff. That kind of I learned the lesson after doing a few simulations, and especially managing simulations and managing them after a year after done initial paper. There was some work for the paper. Then paper has to be modified, things are changing, like you want to rerun the simulation scenarios. So you want to have some environment in which you can run scenarios in more reliable way, like more, I won't say reliable, but rather maintainable way. So for that one, I kind of, initially I did it for myself. I create a small separate repository that is not directly inside the ndnSIM, but rather uses NS3 and ndnSIM routines as external modules and being just linked to them. And inside of that kind of simulation scenario, you can provide any extensions that you would like, separate forwarding strategy, for example. You can add additional application things in that. And again, anything that you would, almost everything that you would like to, and it will be almost easily compiled in almost a breeze compared to the base NS3. And the process is a little bit more complex because you need to first install ndnSIM and then manage the separate repository, and show you a link here, and then do the compilation. But it's easier because it's a separate repository. You can manage that repository in your way, like it's your GitHub. You just put there, and that GitHub or that Git repository contains everything that you need for that scenario. You can write scripts to do processing of the data that you obtained, and you can write a scripts that automatically produce graphs of some kind. So this is the way I was approaching this problem. I kind of recommend doing this way. Whether you prefer to do that way or not, I don't know. But for example, I forgot which one. This is the old one. There's also even the runner script that basically defines how many different things I can have. Baseline. Yeah, so it's kind of I honestly forgot what it is. It's just some kind of scenarios, like all run, and basically running some scripts, specifying initial parameter, potentially splitting them into different threads, because you may want to run scenario not just like sequentially, like, okay, I actually have to step back on this one. NS3 by itself is the single-threaded model. So everything that is happening like in a single scenario, in a single NS3 instance, is done in a single thread. And all the events are happening this way. There are extensions that you can potentially run in multi-threaded environment using MPI, but this is like extensions, and you have to do kind of very conscious decisions of how you actually do that, and it's not working for every possible scenario. So with that kind of limitation, it's actually not fully limitation per se, but rather just a feature of ndnSIM, of NS3/ndnSIM. Because this is simulated environment, and in simulations, you usually want to run them multiple times. Look, you don't want to just produce one result, look, with a specific randomness involved in this process, and just declare that, oh, this is definitive result. No, because there's a lot of randomness may exist in this scenario, and sometimes you actually need to introduce this randomness. For example, like you break some links, introduce some packet losses at specific nodes at random times, or some other types of randomness. So in those cases, you actually want to run multiple times, multiple runs of the simulation scenarios. And now you have an option. You have an option to run them in sequence, like on a single thread, which will effectively waste time, or you can just run them in parallel and then have produced 5 files in parallel in about the same time, and then do the results aggregation. You can do it manually, you can just run all those commands manually, or you write scripts, for example, like this runner script that I was trying to highlight here, that will effectively split the execution per different runs, per different input parameters, and run them in some form in parallel. Before I go to the actual scenario, I just want to go over the very basic, the concept of the scenario inside ndnSIM. So first of all, you can name scenarios in different ways. As already highlighted, you can do either C++, which is I kind of recommend that would be your primary way of doing simulations. Again, if you know for sure that you can do stuff whatever you want in Python, that would be simpler to run, or simple to do modification because you don't need to recompile the whole thing. But again, it has limitations. It may not support all the features. So this is the way you can do this way. For the topology, there are multiple ways to define the topology. We kind of hacked the topology reader, so you can basically create a simple file that defines how many nodes, their locations, some basic properties like how many packets is supposed to be in a queue for different interfaces, what kind of links, what kind of delays on those packets, and pass this file to ndnSIM scenario, and that will automatically create the topology, assign the specific links to the topology, and also install ndn stack on all the nodes that you requested. And in addition, we can also configure different parameters for the NFD stack and for the ndn stack, including different strategies. Like this is very similar how you can deal with the NFD. You have to specify the prefix, you specify the forwarding strategy, either it's one of the standard strategies, for example, this best route, or if you're planning to use any customized strategies for the evaluation, you basically select your strategy, either by class name or by the common name that you can do it. For the FIP, you either do things completely manually, you using global routing controller, and there was actually an option, this is like a separate scenario where you can run NLSR to power the routing, but that one brings additional dependency, and I'm not sure the current state of that scenario yet. And for the content store is the content store. So basically, this is already highlighted it in very basic module. In order to start dealing with the simulation scenario, you just need to create a file. So this is like scenario 1, for example. In that scenario 1, the first step is to include all the stuff that you will be needing in order to write that C++ application, because it's nothing more than just the C++ application. And in this specific case, I want to use the core module. So basically, this includes this simulator class and some other things. I want to use a network module that defines any networking capabilities. I want to use the point-to-point module that defines kind of point-to-point network capabilities, in the sense that it creates net devices and simulated net devices that can send packets directly between 2 different nodes. It's not exactly Ethernet. It's a very simplified model for the simulator. So it's literally kind of virtualized link over which one you can just send a packet between 2 nodes. Point-to-point grid is just for this specific scenario, is a helper to create the grid topologies. Yet another way of dealing with topologies in NS3 in general. And ndnSIM module is simply any NDN related functions that you need to do to have inside this scenario. And then is a standard main function. So you just create the main function, and inside that the main function would be some kind of a meet. What this meet is really depends on scenario. In this specific case, you can define some default parameters. So in this case, because I'm not creating, in this example that I'll be showing, I'm not creating topology using the topology file that defines all the bandwidths. So we have to kind of specify what kind of bandwidths I want to have in this topology. So in this case, I just want 10 megabits per second with the 10 millisecond delay and very small queue of 20 packets. The other line that was missing originally from the scenario that I was showing is just the copy paste this one. It will allow you to specify any standard NS3 command line options to define to see what kind of logins available, and most importantly, to define any variables that we need to define. And the most important variable there is a run. So basically, if you're doing some form of randomization, like random links, random failures, you need to define what kind of run you're running. So it's a run number 1, run number 2, and run number 3. And each different run will have a different initialization for the random sequence. So you don't need to literally generate, it's not a seed number that you may be familiar with, but it's related to the seed number. So look, but again, it's very NS3 like simulator friendly way of defining that I want to do different sequences of random numbers. And again, if you just include this one, it will automatically allow us to specify like minus run a command line parameter to define what run I'm doing. And that's basically it for the initial setup. And then just follow the model that I was showing before, like define a topology. Again, this is one of the ways to define topology. It's like point-to-point grid and nothing more. A grid of 3 by 3 with the point-to-point links. That's it. This bounding box is additional stuff, not really necessary, but it's effectively if you're kind of emulating not point-to-point links, or if you're trying to do some kind of visualization, that will allow us to kind of approximate that. Or if it was some kind of a Wi-Fi module and you were setting up not point-to-point helper, but like Wi-Fi module, that distance would be in meters, and defining how far away the nodes are from each other, like defining different signal patterns. In defining what simulate, and finally run the simulation. So in this case, I kind of requested to run simulations for the 20 seconds, because in some simulation scenarios, you can finish all the events, and in some simulation environment, it's not really possible. So in most cases, for the NDN related simulations, we just install an NDN stack, which is like installing an NFD on the node, which kind of runs forever. Like as soon as you define the stack, it just doing some internal processing. And with that, there's always some kind of events being scheduled, and you have to define how long you're going to run. Otherwise, your simulation will never finish. And this destroy option is not really necessary in this case, because we are just terminating the application, but it's nice to have. And if you're trying to run multiple simulation scenarios in the same file, like in the same instance of the application, then it would provide something. But again, so this was the all around, that was all about NS3 itself. There is nothing ndnSIM involved. And now the actual simulation for the NDN stuff. And as I said, like, you can define prefixes using global routing helper. So in this case, the only prefix that I kind of want to announce in that environment is like /prefix for a specific producer, and producer is, in this case, it's an instance of the node class. Node is a NS3's representation of the node, and I'll try to show this a few examples. NDN stack helper is the main thing to deal with the NDN stack, like to installing them, and in a simple way, and this is, I think, the most common way I'm using this application in this stack helper is just simply installing NDN stack on all nodes in my simulation scenario. This is, I think, 99 or even close to 100% of all simulation scenarios that I'm writing. There are cases when you don't want to install NDN stack on a node, but that's probably a very common case. And then finally, you can, so the nodes has been already created, like using the grid. The only thing that needs to be done now is to get access to some of the nodes and do something on those. Like by installing NDN stack on all nodes, you just install NFD on all of them, and the NFD will be running. You can explore what's happening, but again, without doing anything else, there's nothing else to do. There's no actual things happening. So what you need to do is simply install the application using NDN app helper, for example. Like in this case, this is just a class that provides ability to create instance of application, configure the application, and schedule that application to be started at some point of time. And in this case, I'm installing using the node container. Again, this is just a little bit weird syntactical way. You can install just on a node, but in case you install an application on multiple nodes, you can create a class called node container, add to this class whatever nodes that you think you need this application to be installed. So for example, I got from the grid, I got node from the coordinate 0, 0, and that's the only one I want to install this consumer application. I configured that I want to request data from /prefix, with a frequency of 10, I think it's a 10 interest per second. This is a very rudimentary application. It doesn't do any timeouts or retransmissions. And then I'm installing this application. That's basically it, with one exception that you can actually schedule to start this application and stop this application at specific point of time. And this can be done very easily by just, instead of a semicolon here, put a period and literally write start application at specific time and stop application at specific time. Or you can kind of create a variable that represents all the application being installed and do the same on those applications. And then, again, the basic stuff left is to actually install the producer, because that's what the producer will be. Again, the same process. I think in this case, I even simplified process, just got the node like 2.2 from the grid, created another application helper using the producer, configure this producer that I want to create the responses with a packet size of 1,000 bytes, and install application on the producer. And that's basically it for the process. So when I'm installing the application, again, so this one is using this using NS3 producer and NS3 consumer. In these cases, we're not using NDN face, and therefore we have to actually provide all the routing ourselves. So you have to look very careful because nothing is automatically registered in this case. And you just run it. I'm not going to talk about the Python bindings, but this is, if you have access to the slide deck later, you can just see that if the thing can be supported in Python, the code is literally the same. We just a slightly different syntax for the inclusion, but you still do inclusion of the core, network, point-to-point layout, and ndnSIM. You do the very similar configuration of the default parameters, very similar stuff with the creating a grid, running simulation scenario, and even defined in the meet. This would be almost a one-to-one correspondence. Again, if that's supported, because it's not really supported for all cases. And for the running scenario, that's kind of it. So you just run example, WAF example, and that's kind of already highlighted how it's being run. This one is the scenario that I kind of highlighted, that you can create to allow you to simplify dealing with NDN simulations. So you can put some extensions here If you want extensions, you can put scenarios here that will be automatically compiled against the specified module, and that's basically it. And the way I will be doing this right now, I will just create scenario one. I think it's CPP. It may be a different file. Let me double check. This one, you still need to do configuration. In this case, for now, I'm dealing with the debug mode. So I'm going to be doing it very slow. It configured. Again, the only thing it's doing is detecting that NS3 is installed and checking the compilation flags. And the rest is kind of simple. It's just compiling our code. And then in this case, it just failed to compile because we have a file, but that file doesn't have anything in there. So in this case, what I'm doing, I'm going to be just copy pasting a few things from the slides. I did the inclusion. Hopefully I didn't mess up too much. There's a main file, main method. Else we have a default parameters. Again, not really necessary, so I just only keep one of these. This command line parsing I'll keep, it's useful. For the helper, I'll edit to run scenario. That's at the end. So what else? I'm missing one thing. And for the meat, again, we'll do this. That's how install. And again, I'll try to stop for now and try to compile it. So hopefully it will compile. I don't remember any problems. No. I'll compile in a few seconds. Give me a sec. Like in general, using namespace things is not ideal, and especially problematic in the NDN case because we have NS3 NDN and we have just NDN. Like one referring to the stuff inside NS3 and the other one is referring to the stuff in the actual NDN code base that's been kind of linked together. But in this case, everything is already working. So what I did, I created a main file, do some configuration, the box, and install nodes and some kind of simulation is running. In theory, we can already run this. Again, it doesn't really do anything useful, but we can still run. Again, we can run as a just normal file. It will do something. At this point, kind of meaningless. We can enable a little bit of logging. And if I'm not mistaken, it should be something like this. Nope. It highlighted what kind of things we can include. So this one I was at some point wanted to highlight. Again, this applies only for debug mode. So this information in normal cases should not be used as a metric because you have to, in order to get the logging, you have to run application in debug mode. And in debug mode, it runs really, really slow because it's really getting all this information and all the tracing and other stuff. But it's still useful for at least initial debugging when you're trying to understand what is happening and whether things are working correctly or not. And in order to enable logging, you just need to define the environment variable. In this case, it's nslog, and you simply need to know the module name that you want to enable. How to discover those things? That's a semi-question to you. One thing, you can look in the individual, like in the code base, there are some definitions of the login modules. And I think in one of the examples that I showed before, like in a Scratch folder, NS3 Scratch simulator, it has this nslog component, Scratch simulator, and that would be the log module. And a bunch of other files have this one. And if I open different file, NS3. So basically have a bunch of files. Depending on which scenario you're running, it will have its component for the logging. That's one way. The other one, maybe a little bit better way, is to go to the documentation. And inside the documentation for ndnSIM, as well as for the NS3 itself, it has a separate stuff for the logging components. So in this case, it's just, there's a long table defining all possible log components that you can enable for the ndnSIM. In this, what I'm interested now in CXX stuff, or like NFD stuff. So this one have three distinct things. So there's one is coming from the actual ndnCXX library, if you need to do that. The other one is coming from the NFD, and the third part is coming from the ndnSIM itself. So if I can enable like stack helper, I think this protocol thing, and run that stuff, that should do something. Enable, yeah. So in this case, you can see something happened. Very limited. There are some faces have been created just because the what happens in kind of a scenario. We created a topology, install the stack, and behind the scenes, when you install in the stack, it detects all the physical interfaces that are available on that node. And for each node, it creates the point-to-point face to the other node. It's a point-to-point link. It's creating this direct face towards the other node. And at trace sources, so this is just some logic associated. Like if you, at a later point in time, can want to connect tracing for the modules, then there's some logical tracing. So is enabled to just highlight that some things happen with that. But again, there's nothing really happens. So, and to enumerate, if I remember correctly, you just need to do it this way. And now, NFD folder, enable this one too. So it will show a bunch of other stuff that is happening behind the scenes. Again, because this is NFD, there's a lot of things happening when a face is created. Because there's a command happening, there's a notification about the new phase. So this is why you actually see a bunch of data and interests are happening, even though the scenario itself doesn't really do anything yet. But again, this is realistic thing, so we have realistic environment. Okay, so back to the scenario. Where's my? This is we created topology, install the stack. And a few more things that I'm going to copy from the slide deck is installing the application. So I have this. Good, that's good. That should be good. Let me try to compile. And even though like it may seem slow compared to the compilation of the inside the Scratch folder, this is way faster because it's already compiling right away versus it's checking whether the 3,000 or 4,000 files have been modified before even getting to the compilation of your scenario. But again, we compiled everything, and even this one I'll also now enable. I think I'll just anticipation. Calculate roads, and I think that should be it, and something should happen, and we'll see in a second what's happening there. Okay, we compiled, and I'll try to run the scenario and hope it's not going to crash. It didn't crash, but again, right now, it did something. It did the emulation, or it did the simulation, but seemingly didn't happen. And the thing is, we didn't do anything about the collecting the information. I can, again, enable some of the logging to actually convince you that things are happening right. So consumer CBR. I remember that's the name of the logger for the application. I see the application has been created. I may even enable NDN app to see some of the packets are flowing. So there's interest being sent out, on data being produced. So something is happening. I even see the nodes, but it's still not the information that you want. Like you still have no idea what exactly is happening in the system. So that's the problem. And the way you solve this thing is to obtaining some form of the metrics. So for the login, I already highlighted here. This is the same stuff. And for the metrics that you can obtain, Lisha highlighted in initial part. So there are tons of things that you may want to look in the application. Not all of those things you can right away get from ndnSIM, and you still need to do something in order kind of added a few components in your application that you're dealing with to add a tracing point, or in your application literally open the file, write to the file whatever metric you want to write, and then do the processing based on that. In the simplest cases, when you're just looking at the network level traffic, you can end up just installing the tracer. So we have this L3 Retracer, which collects a bunch of high granular information, low granular, with different level of granularity. So for example, it has raw numbers, but also every 1 second, it gives recalculates the aggregate values. So in what we can do is just compile the scenario again. So this is the disadvantage of C++. We have to recompile things. And I forgot to add NS3 here. Oh, I forgot NDN. Yeah, okay, so that was the simple. So I didn't really need to include this file, but this is a highlight of one important thing, yet another important thing for the ndnSIM. So for the ndnSIM module, it includes a reasonably small amount of headers, basically most of the just ndnSIM stuff. So it would be the tracers, it would be the some of the helpers, and some other few things. But it's not going to be everything that is available as part of ndnCXX, and not everything available as part of NFD. If you need to use those directly, and again, this depends on the scenario that you're writing, you can actually include those things. So it would be, it starts on S3 and ndnSIM, and then literally the path inside the folder. Just to highlight, it compiles, nothing bad happens. And running the scenario again, this one with the Retracer installed. I can run it with logging or without logging. I don't really care at this point. So again, I'll seemingly run the scenario without any parameters, and it seemingly doesn't do anything. But on the other hand, I actually got this file now. And this file is almost 0.5 megabyte for stuff, and now it has tons of information that you can start analyzing. And this file, so the format for the Retracer is kind of simple yet extensive. So it defines the time in seconds. So in this case, it just shows it 1 second, 2 seconds, 3 seconds, because everything happened exactly at those points of time. It defines the node number, phase ID on the node, phase description, if something is associated more specific on that. So what we have, there's internal phase, the one pointed out to the content store. We have a net device phase that is pointing out to another point-to-point link. We have application phase that points to the application. And all is basically not really a phase, but rather just a mark to indicate that some information happens about satisfied interest and something happens about the timed out interest. So you can see within 1 second, 10.4 inches got satisfied, and 0.8 inches got not satisfied. And if you wonder how can you have like 0.8 inches, this is like average number. And we're using here is like a weighted average. So that's why even though we have like an actual whole number of interests, you may get like a fractional numbers. If you really care about the actual numbers, there is a packet row in kilobytes row number column. This will be just not average number of the rate per second, but or estimated something per second, but rather the actual number within 1 second, how many things happened at this point of time. And if I go back to my all faces, in this case, I see there's a 13 satisfied interests that happened at this point of time. And those interests not just include the interest I'm scheduling, because I only schedule 10 interests per second, but also the interest that automatically being generated as a response to kind of creation of the face. So whenever we have a face created, this is very well, the command itself is interest, but then there is a notification interest that's been sent out about things, notification interest, and I think there's a few other things that have been kind of triggered as part of this process. In any case, you can do a lot of manual analysis of this file. This is just an example of the tracer, which may work for you or may not work for you. This really depends on the simulation scenario that you're looking at. You can get a lot of information from this. You can aggregate information if you like. So for example, if you don't want to separate in-out interest, you want to look at calculate the number, you simply need to plug this into some software, like some analytic software that can collapse this information and sum things up and give you a little bit better results, so you don't have that extensive information here. We don't really have recommended way of collecting metrics, nor have a recommended way of plotting graphs, because this is really up to you, the tools that you know, or the tools that you're familiar with. We can give you examples how we did it, but it's no way a recommended, like anything that we can recommend of doing. But I can show you the example here. So this is the graphs that we built using R processing with R, and very basic stuff. I think on the website there are a few examples that we can play with. So simulation examples. Again, these are very basic ones, highlighting pretty much similar concepts, maybe in a slightly different way. Oh, just a highlight. So this is, I think this is the same example that I was playing with right now, highlighting this point-to-point helper, bounding box, if you really need to have a bounding box. But instead of this adding NS3 at everything, I enclosed an NS3 namespace, not like usernames, but rather enclosure. And I had a separate main function that is calling the function in the NS3 namespace. And this way will work. If you do using namespace in NS3, it will not work. It will just, again, complain about the ambiguity between NDN and NS3 NDN. So that's why a little bit weird. And there's somewhere at the bottom, I think there was an example of data processing. Let me find, maybe it's in the other place. Sorry. I distinctly remember. Oh, it was in metrics. Sorry. So if you care about the packet rate tracer, so this NDN L3 rate tracer that I was showing file, there is a little bit more specification of what each column represents. There is also L2 tracer that doesn't track the individual interest in data packets, but rather tracking more like kilobytes and just packets on each individual interface. So it's basically lower level stuff. And for the processing, again, I don't even want to do with R at this point, because it's really, really up to you how you do processing. So with R, you can just read the metric file because it's a tab separated file with the header line. It can be easily read as a table into the R. And you can do all kind of a processing in R and even building some information in R. Or you can do with like GNU-plot or some other plotting software with the NumPy if you prefer using Python applications and so forth. So again, there are a few examples on the slide deck how you can do things. There are a few examples on ndnSIM website that they can show examples of R scripts, how to do very basic processing of the input data, especially with the different tracers that we have, and plotting those stuff. It really depends on the scenario, whether this representation makes any sense for you or doesn't make any sense for you. For the strategy, so the one that I didn't show, that you can select different strategies, basically with the strategy choice helper. In this way, you can use the strategy choice helper to install for a specific prefix, that this prefix has to be associated with the multicast strategy. So in this case, you just specify by name this strategy. And this is exactly as done in NFD, because whenever we create a strategy with NFD, we actually register the prefix of the strategy, or maybe better called the identity of the strategy by name. And this name can be used either with the command, like with NFDC command, to do some strategy selection in real environment, or you can use it for the strategy choice helper installation in this environment. What else? Is the content store somewhere? Before that. In some cases, like especially for very simple scenarios, you can resort of using default routes. So in this case, like if you're simply creating a point-to-point environment, point-to-point link, and just 2 nodes or 3 nodes, and the only thing that you want to have is just send interest to the other node. By default, if you don't do anything, it will not create any routes on those nodes, or you have to do it manually. If you set this parameter set default routes, it will simply create the route towards / towards all the faces that being created. And in simple cases, it's just enough. All that is needed in simple cases. Even for this 3-node topology, when it's connected one by one, like in this environment, it would be pretty much enough of the operations. Another thing that I want to highlight, so this is another strategy I highlighted for the global routing helper. I already gave example of this, so I'm not gonna stop here. And that's the other one that I kind of glanced so you can create a topology using this grid module, like point-to-point grid. This is like very rudimentary, very basic stuff, which you're probably not going to be even using ever. A more realistic example is when you're creating the topology semi-manually. So for this one, we have this format of, this is semi-customized format for the annotated topology reader. I think in the later sections, there will be similar format with additional extension that applies to Mini-NDN. But effectively, this file defines nodes, how many nodes in there, like you can put some comments. For the like wireless simulations, you also need to define the locations, because that would define whatever the propagation of the signal. For the point-to-point connection, you don't really need to do that, only for the visualization purposes, like if you build the topology later. And then you simply define which node connected to which over with which parameters. So in this case, it's a node 0 to node 1 with 1 megabit per second, with a queue of 1, with a 10 milliseconds delay, with a 10 of, oh, sorry, first was a routing metrics. So it's kind of for the global routing. All of the metric ones and all the components are 10. There are extensions of this protocol where you can specify properties of the links using like NS3 specific strings. This may be part of the helpers, but again, like if you get to that point, you better email us, and I will show you a specific example how it can be done. For the basic stuff, for example, the CSU, like simple hubs, this is the way you can define the topology. So, and most of the time we use this file. A few times we kind of download the topologies from like this Abilene topology. I don't know what exactly those topology are. And we basically converted those into this format and basically used it. This is another highlight of how you can do this strategy. So this one, a little bit cheating of not registering the custom strategy that's been created is like a global strategy, but rather just installing the instance of that strategy, just calling it by the instance name. But essentially, it's exactly the same stuff. I wanted to highlight scenario SVS. This is what was created by other presenter for our scenario. So he actually used this scenario folder to create SVS, like a chat-like example simulation scenario. And he literally followed all that was provided. Like this is simulation folder. Within the extension, he actually put the code for NDN SVS. It is mostly the same code. Again, there's usually, if it's a library, usually you may end up just using that library as is. In some cases, you still need to do some fine tuning, specifically for some of the like real-time related items. Like if you somehow using directly boost ASIO, the instance, you're trying to create that instance directly there, you may need to like do some special modifications to avoid using it directly. But again, if it's written carefully with the mind of ndnSIM, then it may be possible, or you need to do small modification later. So as an extension of this SVS, there's an extension as the app, like the basis of the app is still not the full thing. And app in terms of the NS3 and NDN, because app in NS3 environment is the class or instance of the class that has special attributes. And specifically, whenever you create this application that can be installed on the nodes in NS3, it must be of the NS3 application class. Basic requirement, each must have the start application and stop application method implemented. And in those methods, you basically do whatever you want. Like if in this case, you want to start the instance of SVS based chat, then you do something. The other one that you can do for the application is to provide the several attributes. So for the attributes, it's nothing more than something that can be set externally from the scenario. So, and there's a facility to kind of, instead of directly supplying parameters to the constructor of something, you provide those parameters indirectly. And the advantage is you kind of can externally provide the parameters, but essentially it's the same thing. And the other one that you can, this one also you can use the Python to create the application and supply parameters to the Python. Otherwise, it would not be really possible to do that. And that's basically it. There's only other thing left is the actual scenarios. And the actual scenarios basically define what needs to be done in those scenarios. In this case, we just follow the same model. There's a point-to-point helper, a few links, default route, strategy, consumer application, that's creating the chat app, creating the delays, whatever, setting up parameters and attributes that were exposed as part of the attributes that I was just showing. Again, creating another app, installing that another app on different node, starting at specific time, this somehow starting at the 10 seconds, this starting at the 0.04 seconds, and you can also define when do you want to stop the application, like in cases that you want some application to represent that something is running and stopping at a specific point of time. Then you can add the FIP helper to add specific routes if you don't want to only rely on the pre-computed routes, or you don't rely on default routes. So this one will be the kind of semi-dynamically, semi-manually defined routes. This is a calculation. Sorry, so this is the static routes, and a global routing helper will calculate routes defined through this at origin star. So now ndnSVS that was defined for the multicast prefix is being announced everywhere. There's no need for the announcement for the multicast prefix, so it's everybody's can send interest in that prefix. And for the unicast prefix, which will be this node 1, node 2, is something related to that. I think in this case, we don't set up any tracers, but again, I can just compile the stuff. Okay. To be fair, I'll just recompile from the scratch. This one is a little bit slower to compile because it still includes extensions. All those ndnSVS still need to be compiled, at least for the first time I'm doing it. There's some producing some warnings, but it has compiled when I tried it last time. So now it compiled with an application. I can run it and see nothing. I mean, there is something that's happening. And again, this highlights another approach how we can do the tracing. So you don't have to rely on this L3 tracer. You don't have to rely on the NS3 provided tracer. What you can simply do is to print out whatever the necessary parameter on the standard output. So that would be the one way, and then redirect the standard output to somewhere and do the processing this way. Or you can literally open the file and supply this file handle to all the instances, or just reopen the file, or open multiple files per instance and store information in there. And in this case, it just notifying when the information received when the information was published, and when that information was received by the other node. So kind of very, very basic the scenario of like creating the chat, publishing the chat, and receiving chat from the application. Oh, sorry. This is again highlighting what Lisha was talking about initially, especially for the transport evaluation, is the separation between knowledge about something happened and message is actually received. So I believe in this case is notification about, I may be wrong, like Varun can correct me here. So in this scenario is assuming that as soon as I'm getting the notification about the data availability, about the publishing data, I'm also trying to receive this information. And this is the aggregate number. The time I'm getting here is the time I'm kind of aggregate from message being published initially, like somebody type in a message, to message being notified that it exists, and the actual message being received. So there's like two processes that doesn't have to be combined at the same time, but in this specific scenario, it made sense to combine them at the same time. So this is this. So basically, this highlights the end result of chat simulation. So this is the last one that we wanted to talk. Try it out. Like if you haven't tried with ndnSIM, try to think what, at least this presentation and this short demo highlighted how you can use ndnSIM. It not necessarily can be used for everything that imaginable, but if you're trying to kind of evaluate a network related or some application related logic in your NDN app, ndnSIM can be used, and you can easily create reasonably large topologies. I'm trying to avoid using a specific number because it's really kind of for ndnSIM as NS3, it really depends on like what you're simulating. So if you have very few events generated, like very small traffic, you can create a huge topology of thousands, maybe 10,000, 100,000 nodes, and simulate them in a reasonable amount of wall clock time. Or if you're trying to simulate a lot of traffic, this one, like if you try to do it with very large topologies, it will just take forever to run even on a very powerful machine. But again, you have to try it out and see whether it's working or not working, or how long simulation you can explore. Check our mailing list. There's a lot of questions. Can go there and we'll try to answer them. We really want you to also contribute to ndnSIM. So for this one, I suggested here to submit code to Garrett. If that's a little bit kind of high point for entry, we also accept a contribution if you submit a pull request on GitHub. We'll basically just convert them to our internal review process to Garrett and eventually merge this stuff.